Today let's review the moisture content. Even though I have a title called drawing, that's the context we are going to learn moisture content. These are basically slides from the moisture content slides we used in 225. I deleted some of the extra slides, kept the key ones. You need to be aware of the standard that is posted on the blackboard. So today let's review the moisture content. Okay. There are two methods. You can express the moisture content in wet basis small m or the dry basis in capital M. First, if a product is there and if its total mass is this, and let's say this is the mass of the water, this is the dry matter, then the total mass equal to the mass of the water plus dry matter. The wet basis small m is equal to the mass of the water divided by the total mass, whereas the dry basis capital M equal to the mass of the water divided by the dry mass. Which is higher, the wet basis or the dry basis? Because the denominator is big, the wet basis is small. Because the dry matter denominator is small, this is higher. Okay. So again, here is the formula. The mass, the moisture content in wet basis is equal to the mass of the water divided by the total mass, which is nothing but the mass of the water plus dry mass. Here is the dry basis. It is very important for you to understand the relationship between the two. The capital M is big. This is the way I always remember. So if I want to calculate capital M, the only difference is whether it is minus or plus. Because I know that the dry basis is big, the denominator has to be small, that's minus m. Similarly, small m equal to m divided by 1 and m, whether should it be plus or minus? Because the wet basis is small, the denominator is high, I put plus. That's how I remember the relationship. You also need to understand that this moisture content is expressed either in decimals or in percentage. So if you multiply by 100, you get the percentage, right? So if you are writing without any percentage, I would assume that it's percentage, it's a decimal. You need to put a percentage to know that it's a percentage. And either you need to use the right symbol, or you should always say whether it is a wet basis or a dry basis clearly on the exam, so that there is no confusions at all. The wet basis is the one commonly used colloquially by the common people in engineering and other stuff. However, in scientific people like to express the moisture in the dry basis. The major reason for that is, let's say you have a process, let's call it as a dryer. If the wet product is getting in and if a dry product is coming out, the dry matter remains constant, but the amount of water changes, right? Whereas the dry matter remains the constant. So it's better to have the denominator constant, right? So that's why in scientific literature, people tend to use a lot more of the dry basis moisture content. But in the colloquial common terms, we use the wet basis commonly. But they both have exactly the same relationship. When you know one, you can determine the other by using the relationship we saw just before. This is an extremely important point. We need to understand equilibrium moisture content and the equilibrium relative humidity. If you have a room or a chamber And let's say I put a food product. Let's say I put a cheese. Okay. And I leave it for a few days. What happens? If the dry is air, there is going to be a transfer of moisture from the cheese to the air, and it will continue to happen, and then at some point an equilibrium is reached. The equilibrium is a condition at which there is no transfer of the moisture between the air and the biological material or the food product. That is known as the equilibrium. At that condition, probably the cheese is dried out. At that condition, that moisture content is known as the EMC, or equilibrium moisture content. That relative humidity of the air is known as the equilibrium relative humidity of the air. And there exists a good relationship between equilibrium relative humidity and the equilibrium moisture content. The same thing holds for the other way too. So in a room, let's say if I have a cracker and a dry cracker, and then let's say it's a very humid, it's raining all the time, then there is going to be the movement of the moisture from the air into the cracker. The cracker is going to get soggy. At some point, it doesn't take any more moisture. At that condition, the moisture content of the cracker is the equilibrium moisture content. The humidity of the air is known as the equilibrium relative humidity. And this relationship is true for at a given temperature. Okay, if the temperature is different, it's going to be different, right? So what is a relative humidity, which we already studied in the psychrometrics? The relative humidity is a measure of the moisture in the air. More usefully, this is the way I would like to understand conceptually. The relative humidity is the ratio of the water in air. This is also known as the humidity in terms of air, right? It is the ratio of the humidity in the air at present temperature relative to the maximum water the air could hold. Okay, so at saturation, the relative humidity is 100%, right? One of the key things to understand is the humidity ratio of the air. The humidity ratio of the air is nothing but the moisture content in dry basis. So if I try to write using my pen, let's go to the next one. So the equilibrium relative humidity is, now my pen is writing, let me go through again. So the humidity ratio, if you remember on the psychrometric chart, the humidity ratio is on the y-axis. The units are pounds of water by pounds of dry air, right? That's nothing but the moisture content in dry basis, right? Whereas the relative humidity are these curvature lines, right? Okay. So there exists a relationship between equilibrium moisture content and the equilibrium relative humidity. So if I plot ERH versus EMC, so if I store a food product in a very, very dry, humid conditions, the product is going to dry out and maybe stabilize at pretty low moisture content. And if I store it at a really high humidity, the product is going to absorb moisture and it's going to have a higher moisture content. And there exists a relationship, and it's typically sigmoidal. Okay, And this equilibrium relative humidity is also known as the water activity is the equilibrium relative humidity by 100. Okay. One of the key things you guys need to understand is the typical moisture content of the air or the humidity ratio of the air is about less than 3%, right? The typical moisture content of the air, right? The typical moisture content of the food product can be pretty high. Okay. So the moisture content of a food product, let's say in a wet basis, let's say it's a 0.8 or 80%. The moisture content in dry basis is 0.8 divided by 1 minus 0.8. 0.8 divided by 0.2 equal to 4 or 400%. So it's pretty high. The moisture content of the food is pretty high. Pay attention, the equilibrium condition is not the one at which the moisture content of the food is equal to the moisture content of the air. It will never be equal, right? So the moisture content of the food is not going to be equal to the moisture content of the air. Rather, the equilibrium is defined when the moisture content of the food is in equilibrium, right, with the relative humidity of the air, right? That's the key thing you guys need to understand. Lot of people mistaken it, but that's not equal. You need to understand that. So we call this as an isotherm because this is at a given temperature. If the temperature changes, your relationship might change. So that's why this is commonly known as isotherms. So here are the examples of the isotherms. This is the shelled corn. At 0 degrees Celsius, it looks like this. As the temperature increases, the curve is shifting down. Why is that? How do I interpret this graph? I can interpret it in two different ways. Okay. So let's say I am storing the food product at 80% RH. Okay. And if it is at a very low temperature, the product moisture content will be pretty high. The corn moisture content is going to be 25%. But if it is at a high temperature, it will try to dry out, right? So the moisture content is going to be lower. So for a given RH, raising the temperature is going to reduce the equilibrium moisture content. The another way to read that is, if I want to store the corn at 15% moisture content, at 0 degrees Celsius, I can store it at, let's say, like a 42% RH. Very dry environment. Whereas if it is 10 degrees Celsius, that's about 52. If it is 30 degrees Celsius, that's about 60. At 50 degrees Celsius, that's about 70% RH. So what that says is, if I want to store the corn at 15% moisture content, at a higher temperature, I can even store it at a humid temperatures, humid relative humidities. And if it is at a colder temperature, I have to keep it in a relatively dry environment, less humidity. So that's the kind of the relationship we are trying to do it. So the ASAB standard I posted on the blackboard, it has for us curves like this. For a different moisture content, different relative humidity, how does it look like? Okay. And they also gave it in different tables. For example, for barley, they gave it as 2 tables for a temperature range of this. So as the temperature changes, the relationship changes. They also fitted a multiple different equations between the ERH and EMC. and determined these constant ABC, and then they have tabulated it. So here are the examples. So here is a barley. You use the equation B. Here are the constants ABC. Why are we bothered about it? Why do we need to learn about it? Number one, if we want to dry corn, we need to know the initial moisture content. What is the desired moisture content? We need to be able to estimate how much moisture I want to remove. That's number one. And another thing, if I have a grain bin, right, and if I want to dry the corn, and if I am blowing the air, as the air going up, the air temperature is dropping, yet relative humidity is increasing, right? And similarly, the corn temperature is dropping and its moisture content is reducing, right? And as the air humidity keep on increases, at some point it may say that I can't absorb any more moisture from you because you are already in equilibrium with me, and then it may leave, right? So you need to understand the dynamics to determine how long you should operate a fan to dry the corn. So that we are going to study on the upcoming chapter. So you do need to understand the equilibrium moisture content and the equilibrium relative humidity of the materials in order for those to do the calculation. And as a take-home message, couple of things are: the dry basis moisture content is higher. The wet basis moisture content is typically the values are lower. The wet basis moisture content is always less than 100%. The dry basis moisture content can be greater than 100%.